So let's take a look at some more related rates. So in the previous video, we saw that the rate of change of the volume of the sphere is related to the rate of the change of the radius of the sphere. So how does this work with other solids like cones? Oil leaks, sand piles, pouring something, coffee pours, like this is a coffee filter. There's a lot to explore. So the cone at the right has a height of 15 inches and a radius of 5 inches. So first of all, one thing that we need to remember is that the height and the radius of a cone are proportional. So what does that mean? Well, it means that ratio of r over h is going to stay the same no matter what that height of the cone is. That ratio is going to have the same proportion to it. So when the water is filled to a height of 12 inches, what will the radius be? So we know that right now we have a proportion of 5 to 15. And so we want to know if the height is 12 inches, what is the radius going to be? I can actually use an r. And if we solve this, we're going to get that r equals 4 inches. So basically what we've done is we've looked at similar triangles. We have the radius and the height of this triangle, and then we're looking at this smaller triangle, and we knew that the height was going to be 12 inches. We just had to find the radius was 4 inches. So now when the water is filled to a height of 10 inches, what will the radius be? So we can set up a similar proportion. Solving this one, we're going to get that r equals 10/3. So how would we describe the relationship between the height and the radius of this cone? Pause the video and write down how you would describe it. So we see that the height is 3 times the radius, or we could say that the radius is 1/3 of the height. Writing these as two simple equations, we could say h equals 3 times the r, or r equals 1/3 of the h. All right, so number 2, the cone from above is filled to the brim with water. Water is draining from the cone at a rate of 10 cubic inches per minute. Write an equation that relates the variables in the problem. So I'd like you to pause the video and do part A, and while you're at it, write down any other information that you can get from the problem given and what you've written for part A. So it's a cone, and we're dealing with a volume. So again, pi r squared is a circle because it's a cone, and then because it tapers, it's going to taper basically 1/3 and then times the h. So volume of a cone is 1/3 pi r squared h. The other thing we know from the information given is that water is draining at a rate of 10 cubic inches per minute. And if you're not really sure what variable that would be, think cubic inches is going to be a volume. Cubic would have 3 dimensions. So the dV dt is negative 10 cubic inches per minute. So now which of variables in that above equation are changing and which are staying the same? Well, as water is draining, is the volume staying the same? Is the radius staying the same? Is the height staying the same? Nope, they're all changing. None of them are staying constant, but they all are going to be functions of time. As the minutes tick on, they all change. So how is this different from yesterday's problem about the helium balloon? Well, the helium balloon was what shape? It was a sphere, and so the volume depended only on the radius. The cone's volume, on the other hand, is going to depend on the radius and the height. Okay, so let's see if we can make our problem look a little bit more familiar and manageable. I've just rewritten the problem that we had back on the previous page from 2a. So now we're asked to rewrite our equation in 2a so that the volume is in terms of the radius, only in terms of the radius. It could have just as easily asked if the volume was in terms of just the height, but we're going to rewrite this so it's in terms of just the radius. So I'd like you to go back and look at what we have written down for 1c. Go ahead and pause the video and go ahead and do parts A and B. So remember that h equals 3 times r, so replacing my h with that 3r, and then simplifying, 1/3 times 3 gives me 1, and r squared times r is r cubed, so my volume is pi r cubed. Taking the derivative of both sides with respect to time, so the derivative of v is 1, but with respect to time we need that dv dt. Equals the derivative of, again, the chain rule, so 3 pi r squared, the derivative of the inside, that r, with respect to time, is going to be dr dt. So now at the instant when the radius is 4 inches, what is the rate of change of the radius? So this is where we start to plug in everything that we know. So again, if we look back to at the very beginning of this problem, remember we wrote that our dV dt equals negative 10 cubic inches per minute. So we can just plug that in. That's the rate that the water is flowing out. Equals 3 pi, well, it's telling us right here that my radius is 4, so times 4 squared, dr dt. The only variable we left have in that is the dr dt. So go ahead and pause the video and solve that. So when we go ahead and solve that, we get that the radius is changing at a rate of negative 0.066 inches per minute. Okay, so part D, at the instant when the radius is 4 inches, what is the rate of change of the height? So we can go through this whole process from part 3 again. Go back up to part A and write the volume in terms of the height. So replacing the R with 1/3 h. Go through ahead and differentiate that. Otherwise, when the radius is 4 inches, well, I know that there's a relationship between the height and the radius. So I have h equals 3r. If I differentiate both of these with respect to time, I get 3 dr dt. But since the radius is at 4 inches, I know what my rate of change of my radius is. So go ahead and plug in that negative 0.066. We get 3 times negative 0.066. And we get that our dh dt is negative 0.198 inches per minute. So the height is changing at a rate of negative 0.198 inches per minute. So these important ideas for today are basically going to be very similar to the important ideas from yesterday. It's going to go through the steps to solve these related rates. There might be a little bit different in the order, but these are basically the steps for all of the problems. The first thing, draw a figure and label the quantities that don't change if you can draw a figure. So remember yesterday we had that cylinder, and as the water raised or lowered in that cylinder, my radius didn't change, so we were able to plug in that radius right away. Identify rates of change that are known and rates of change that are unknown. So oftentimes you're going to have just one thing that you have to find. But for example, this last problem, it could have asked us to find the rate of change of the height and the rate of change of the radius, which we did. Write an equation that relates all the quantities or variables. This is usually going to be a formula. And then finally, differentiate both sides with respect to time. So you're going to be using implicit differentiation. And then evaluate by substituting in your known values and solving. So now let's go ahead and take a look at another example or two. So the first problem, translate each of the following sentences into mathematical statements using derivatives. I want you to go ahead and pause the video and do these 3 problems. The height of the water is increasing. That means the height of the water is changing. So the dH dt is the change in the height with respect to time equals 2 feet per hour. Water is pouring into the cone at a steady rate of 7 cubic inches per minute. So again, if you don't remember, remember that cubic inches has to be a volume. It has 3 dimensions. So dV dt, the change in my volume, equals 7 cubic inches per minute. And the radius of the surface of the water is decreasing 1.5 inches per minute. So radius, the change in the radius, dr dt, is negative 1.5 inches per minute. And our last problem, a conical tank has a height of 10 feet and a radius of 6 feet. Determine the relationship between the height of the water, h, and the radius of the surface of the water, r. Go ahead and pause the video and write that relationship down. So remember, cones are proportional, the radius and the height. So r is to h as 6 is to 10. So it simplifies to r over h equals 3/5. We're going to need to know what r equals or h equals, so solving that equation or that proportion for both r and h, I get r equals 3/5 h or h equals 5/3 r. Okay, so now write a formula for the volume of the water. You can refer back earlier for number 2 for that, and then I want you to go ahead and do part 1 and 2. Write as a function of h alone, and write as a function of r alone. Okay, so water is pouring into the cone at a rate of 5 cubic inches per minute. How fast is the radius changing when the height of the water in the cone is 4 inches? There's a lot going on in this problem. Another way to organize yourself in sometimes of these problems when there's a lot going on is to write down what you know and what you need to find. So what do we know? Well, we know that it's pouring in at a rate of 5 cubic inches per minute. That's the volume. So we know that my dV dt equals 5 cubic inches per minute. We also know that we need to find how fast the radius is changing, so dr dt. We need to do this when the height equals 4 inches. Since we have to find the radius, the rate of change of the radius, then we need the equation that has just the radius in it. So the one from right above, the volume equals 5/9 pi r cubed. So now go ahead and pause the video and differentiate that and substitute in everything that you know and come back if you run into a problem. So we differentiate it and simplifying it, and I get dv dt equals 5/3 pi r squared dr dt. So now I'm going to plug everything in that I know. dv dt is 5 equals 5/3 pi. Oh wait, I don't have my r. Did you remember that up above we know that when h equals 4, r equals 3/5 of h. So r equals 3/5 times 4. Oh, so my r is going to be 12/5 squared dr dt. Now go ahead and finish that problem, solve that for dr dt. So plugging everything in we know, keeping that pi until the very end if possible, so we are rounding our decimals as late as possible in the problem. We get that dr dt, the rate of change of the radius, is 0.166 inches per minute. All right, I hope this isn't too confusing. Come to class with questions if it is.